Have you ever wondered if our vast universe balances its books to zero? That's right, I'm talking about the zero-energy universe hypothesis, a concept as perplexing as it is fascinating. Let's dive in. In a nutshell, this hypothesis suggests that all the positive energy of matter in the universe, think stars, galaxies, and particles, is perfectly counteracted by the negative energy of gravity. This balance, if true, would mean that the universe's net energy equals zero. So, where does this idea come from? During World War II, physicist Pascual Jordan proposed that energy conservation might not prevent a star from popping into existence from a quantum vacuum fluctuation. According to him, the positive energy of a star's mass could be exactly cancelled out by the negative energy in its gravitational field. Fast forward to the 60s, and we see Richard Feynman delving into these calculations, laying a foundation that would inspire future physicists, including Edward Tryon in 1973, who suggested that the entire universe might have emerged from a massive quantum fluctuation. Now let's touch on challenges. The total energy calculations are sensitive to the choice of coordinate systems, and as Alan Guth showed in 1987, gravitational energy is indeed negative. Stephen Hawking even introduced cyclic time in 1988 to explain the generation of both positive and negative energies. What does this mean for us and our understanding of the universe? If the universe really started from zero energy, it's like a grand cosmic magic trick, something emerging from absolute nothingness supported by fleeting quantum fluctuations. Yet not everything is neatly packed into this hypothesis. We still wrestle with the mysteries of dark energy and dark matter, which currently don't fit into the zero energy framework. In conclusion, the zero-energy universe hypothesis isn't just a scientific curiosity, it challenges our very perceptions of cosmos and creation. It's a mind-bending exploration into how something as vast as the universe could arise from nothing at all. Now that we've delved into the zero-energy universe hypothesis, you might be wondering, how can we actually test this cosmic idea? Testing the zero-energy hypothesis is a fascinating challenge as it involves probing the fundamental nature of the universe itself. While direct experimental tests are elusive due to the cosmic scale and complexity, scientists have proposed several indirect methods and observations that could shed light on this intriguing idea. Let's explore a few of these methods. First, there's the cosmic expansion rate, often referred to as the Hubble parameter, h_0. This parameter describes the rate at which the universe is expanding. If the universe has zero total energy, the expansion rate should be consistent with the critical density required for a flat universe. By observing distant galaxies and their redshifts, astronomers gather valuable data to estimate h_0. Next, we consider the cosmic microwave background, or CMB. This radiation is the afterglow of the Big Bang, and its temperature fluctuations reveal the distribution of matter and energy in the early universe. Precise measurements of the CMB can help determine the overall geometry of the universe. A flat universe, consistent with zero total energy, would leave specific patterns in the CMB. We also look at the large-scale structure and galaxy clusters. The distribution of galaxies and galaxy clusters across the cosmos reflects the underlying gravitational field. If the universe has zero total energy, we'd expect to see large-scale structures consistent with a flat geometry. Observations of galaxy clustering and cosmic filaments provide valuable insights. Dark energy and accelerated expansion present another puzzle. Dark energy, responsible for the accelerated expansion of the universe, remains a mystery. If the universe has zero total energy, dark energy's contribution must be precisely balanced by other forms of energy. By studying the expansion history and the behavior of dark energy, scientists hope to find clues. Gravitational waves and black holes offer yet another avenue. Gravitational waves, detected from merging black holes and neutron stars, reveal the dynamics of strong gravitational fields. If the universe has zero total energy, the gravitational wave's properties should align with this balance. Upcoming observatories like LISA, the Laser Interferometer Space Antenna, will explore this further. Quantum fluctuations and vacuum energy also play a crucial role. Quantum fluctuations in the vacuum can lead to temporary violations of energy conservation. If the universe emerged from such a fluctuation, it would support the zero-energy hypothesis. High-energy particle physics experiments might indirectly probe vacuum energy. Finally, we have energy conservation tests in local systems. While the universe as a whole is challenging to test, we can examine energy conservation in smaller systems. Laboratory experiments and precision measurements can verify energy conservation principles. In conclusion, while testing the zero-energy hypothesis directly is challenging, these indirect methods and observations offer promising avenues. Each piece of data brings us one step closer to understanding whether our universe truly balances its cosmic books to zero. Now that we've delved into the methods of testing the zero-energy universe hypothesis, let's explore the fascinating concepts proposed by Stephen Hawking and Nathan Rosen. Stephen Hawking's Cyclic time, 1988. Stephen Hawking, renowned theoretical physicist and cosmologist, delved into the nature of time and the universe. His cyclic model aimed to address fundamental questions, including the generation of both positive and negative energy. Here are the key points of his proposal. Cyclic universe. Hawking envisioned a universe that undergoes cycles of expansion and contraction. These cycles repeat indefinitely, with each cycle beginning from a singularity similar to the Big Bang. Positive and negative energy. During expansion, matter and radiation contribute positive energy. As the universe contracts, gravitational potential energy becomes negative. The net energy remains zero across the entire cycle. Avoiding cosmic singularities. By introducing cyclic behavior, Hawking aimed to avoid singularities such as the initial singularity of the Big Bang. Instead of a single beginning, the universe experiences a perpetual sequence of expansions and contractions. Quantum effects and tunneling. Hawking invoked quantum effects to allow the universe to tunnel from one cycle to the next. Quantum fluctuations could trigger a transition from contraction to expansion. Challenges and open questions. The cyclic model faces challenges related to entropy, the arrow of time, and the nature of the singularity. It remains an area of active research and speculation. Nathan Rosen's closed universe, 1994. Nathan Rosen, a physicist known for his work in general relativity, explored the concept of a closed universe. Here's what his proposal entails. Closed universe geometry. A closed universe has a compact spatial geometry akin to a hypersphere. It loops back on itself, meaning that if you travel far enough in any direction, you eventually return to your starting point. Total energy balance. Rosen and J.V. Jory demonstrated that in a closed universe, the total energy, combining matter, radiation, and gravitational energy, can be precisely zero. This balance arises due to the curvature of space. Inflation-driven matter generation. Inflation, a rapid expansion phase in the early universe, could lead to the creation of matter and energy. As the universe expands, quantum fluctuations generate particles and fields. This process contributes to the overall energy content, cosmic cycles, and stability. Unlike Hawking's cyclic model, Rosen's closed universe doesn't necessarily involve repeated cycles. Stability and the avoidance of singularities are central to this concept. Both Hawking's and Rosen's ideas offer intriguing perspectives on how the universe might balance its cosmic books to zero.